What is the quantum Fourier transform explained? Have you ever wondered how quantum computers can solve complex problems so quickly? One key player in their power is the quantum Fourier transform. Let's break it down together. The quantum Fourier transform is the quantum version of the classical discrete Fourier transform. It operates on the amplitudes of a quantum state, which is represented by qubits. When you apply the quantum Fourier transform, it transforms one quantum state into another. This happens through a linear transformation that maps the input vector of complex amplitudes to a new vector that represents the Fourier transform of the original state. If you have a quantum register with n qubits, the quantum Fourier transform works on a vector of length n, which equals to raise to the power of n. In simpler terms, the more qubits you have, the larger the vector you can work with. Now, let's compare this to classical computing. The classical discrete Fourier transform converts a vector of complex numbers into another vector. Each element in this new vector is a weighted sum of the original elements multiplied by complex roots of unity. The quantum Fourier transform does this directly on the quantum state. It uses quantum gates to perform the operation much more efficiently. One of the standout features of the quantum Fourier transform is that it transforms a quantum state into another quantum state. The coefficients in the new state are obtained by applying the Fourier transform formula to the original coefficients. It introduces specific phase shifts that correspond to primitive roots of unity, which are complex numbers that satisfy a certain equation. When we look at speed, the classical fast Fourier transform runs in time proportional to n times the logarithm of n. In contrast, the quantum Fourier transform can be implemented on a quantum computer with only n-squared operations. This means it offers an exponential speed advantage for larger inputs. The quantum Fourier transform is essential in several important quantum algorithms. For instance, it plays a critical role in Shor's algorithm, which is used for integer factorization, and in quantum phase estimation. These algorithms relying on the ability to efficiently extract periodicity and phase information from quantum states. However, there is a catch. When you measure the output state of the quantum Fourier transform, you only get one outcome probabilistically. This means the complete Fourier transform information is not directly accessible. To get the full picture, you need to perform repeated measurements and additional algorithmic steps. In practice, the quantum Fourier transform is implemented using a series of quantum gates. These include Hadamard gates and controlled phase rotation gates. They are arranged in a specific way to produce the desired transformation on the qubit register. This structure makes the quantum Fourier transform a fundamental building block for quantum software and algorithms that deal with problems involving periodicity, frequency analysis, and eigenvalue estimation. In summary, the quantum Fourier transform is a powerful tool in quantum computing. It extends the classical Fourier transform into the quantum realm, allowing for exponential computational advantages in specific problems related to quantum computing hardware and software.